Okay, we'll continue with our VLSI design. So you have covered 3 units, Unit 1, Unit 2, Unit 3. Now your 4th unit is related to subsystem design. So in Unit 1, we have seen our VLSI design is related to fabrication of integrated circuits. So an integrated circuit consists of a miniaturized chip having active and passive components. So active components can be diodes, transistors. Passive components are resistor, inductor, capacitor. So together they complete some design, some functionality is implemented. So depending upon that, you have analog ICs, digital ICs, and mixed signal ICs. So analog ICs, we have seen amplifier oscillators where they can process analog signals. Digital ICs, they can process digital signals like logic 1, logic 0. Mixed signal ICs, where they can process both analog and digital, such as your A to D, D to A converters. So coming to IC designing, you have seen the basic element of your design. Anything, it is a active or passive element. So they are transistors, diodes, and this RLC components. That part you have seen in the first part, and fabrication of an integrated circuit was studied. So then in second part, the electrical properties. In the third part, we have seen the wiring capacitance, delays. So in fourth unit, we are seeing the IC designing at subsystem level. So integrated circuit, IC at subsystem design level. So first unit is related to transistor level. It's fabrication. So in the layers of silicon, what is happening? Okay. So how layers are formed in the silicon. Second unit, its properties, layouts. So logic design, circuit design, layout design. So these are the different stages of a VLSI designer. In fourth unit, it is subsystem design. What is subsystem? Here you are going to study two topics in subsystem. One is data path. So because any design you want to implement in an IC, you can't just randomly pick the design and go on forming the layers. There must be some strategy. So to implement that, so all VLSI designers, they follow this method called subsystem design methods, the data path and hierarchy. So what is hierarchy? They built in a top-down design approach. Okay, so what is your top module? What are the sub-modules? What are the sub-modules? So like that, they go on build the modules and they can combine together, they complete your IC. So every IC logic, the logic designer analyzes the logic, and those logic are implemented used by some components of circuit designer, and layout designer creates the layout of that. So basic requirement of our IC design is we have to manufacture an IC having less area, low power consumption, high speed. So these are the three criteria. So these criteria are met for an IC if its subsystems are also optimized. So what are the subsystems? Any IC, depending on the IC, it can have an oscillator, it can have a mixer circuit, it can have an amplifier circuit, it can have a memory circuit, anything. So within an IC, there are so many subsystems. Those all subsystems together implement your functionality. So if you see any DSP FFT algorithm or any multimedia applications, audio video codecs, so all they have some internally all the components, and those components are optimized such that its subsystems are optimized. So a VLSI designer is going to study in fourth unit what are the subsystems you can come across in an IC and how they are optimized. So we are just seeing the functionality, but in real time designing, you have to see that if you consider one subsystem like oscillator. So what are the different methods of designing an oscillator and how it satisfies less area, low power consumption, high speed. So if all subsystems are optimized, then your entire IC is optimized. Then only you can go for designing at the fab level. Okay, and after it is tested, you can see that your IC is a low power, low voltage IC meeting your requirement. So this subject is in unit 4. The subject is similar to your switching theory logic design, where you can come across all analog, all combination and sequential circuits. So here also you are going to see so many combination sequential circuits, their logic, how they are implemented. But here we are not going to study what is the optimized design. The basic requirement of fourth unit is subsystems must be optimized, but we are seeing its architecture from the designer side. They are the optimized designs. But in real life, when you become a VLSI designer, you have to see that your subsystem is optimized for area, power, speed, and these three major parameters together, they also satisfy the other two requirements. One is cost and performance. So low cost and high performance. Low cost, high performance, less area, low power, high speed. So this is designed for all the subsystems. So unit 4 subsystem, first part is data path. So data path tells it is the design strategy where you can see how you can implement design with meeting these requirements, how your data lines and control lines will be designed. And hierarchy tells any design must be analyzed as top-down design methodology or bottom-up. Generally, we mix. Now we are going to mix them while designing. So that is your unit 4 subsystem designing. So in subsystem design, so the first is we are going to see what is our objective. So objective is design consideration. So how the problem is analyzed and it is and the corresponding solution. And for our subsystem design, we are considering the basic architecture is a digital processor structure and its data path architecture and its bus architecture. So your example of digital processor structure must be analyzed in terms of its data path and bus architecture. And also we are going to study various subsystems. So this is a very simple unit where you are going to directly read the design of corresponding subsystems. So one subsystem you are going to study are these are shifters, adder, ALU, multiplier, parity generator, comparator, 0-1 detector, and counter. So from STLD point of view, you are going to see what are the alternate designs. If you design a 3-bit counter, what is the 4-bit counter? Synchronous counter, asynchronous counter. But here in this unit, you have a ready-made design. Only thing is when he is asking in the exam, write about shifters or adders. There is a ready-made architecture in the textbook. We have to just reproduce it. Only thing is we learn how it is operating. So if there is a adder, what is an adder? How to speed up its addition operation. Multiplier, signed multiplication, unsigned multiplications, like that. So very simple unit, subsystem design. So subsystems, for subsystems, what are the design considerations? The general considerations we are going to cover is, one is you have to see that your IC is having lower unit cost and its lower unit cost, higher reliability, lower power dissipation, lower weight, and lower volume. So these are the same as our 5 entities for an IC designing. The same entities are covered for subsystems, lower unit cost, higher reliability, so high performance. Okay, so whatever you design, it is highly reliable and it is meeting the requirement. Lower power dissipation, lower weight, and lower volume, and better performance, enhanced repeatability, and reduced design time. So these are the general considerations for subsystems. So what is the problems for our designing is we cover 3 problems. One is your IC, whatever we analyze, that is both at subsystems and IC level. So you want to design a complex system in a reasonable time and with reasonable efforts. So what is reasonable effort? You want to implement one asynchronous counter or synchronous counter. In the library, if you are having a ready-made architecture, you can use the same architecture. Okay. So no need to reproduce again. So those subsystem you can use the same architecture. And also you have to decide the technology. What is technology? Whether you are implementing subsystems with NMOS technology, CMOS technology, BiCMOS technology, or any alternate gate circuits, which you studied in the third unit. Alternate gate circuits, pseudo NMOS, differential cascade voltage switch logic. So those are the alternate designs. Why we go for again alternate designs? Meet the 5 entities: less area, low power, high speed. So our complex system should be designed in a reasonable time and with less effort. So this is the first problem we are creating for our design strategy. Okay, so our IC or subsystems must be designed with this parameter. Next, whatever the architecture you select, that must take full advantage of VLSI technology. What is the full advantage of VLSI technology? You can do a scaling. You have one topic called scaling of VLSI technology. So where your supply, power supply is reduced, corresponding length and width are reduced, so that within a small area you can keep more transistors fabricated. So certain design techniques or certain transistors, if you are going below that limit, they might not operate properly for certain technologies. So you have to see that whatever the architecture you select, like if you want to implement an adder, you can implement by various methods. Okay, so that architecture selected must be such that it is taking full advantage of VLSI technology. Even if you scale also, that architecture should perform very well. Even if you increase it, like a 4-bit adder, you want to make it 8-bit adder. So it must not be such that it is creating more delays and your logic of design uh, in, uh, is corrupted. Okay, so architecture is selected for a specific subsystem must be taking full advantage of VLSI technology. And everything, whatever you manufacture, the IC manufacturer must be tested, implemented on a silicon. So for a subsystem, these 3 problems we have created and corresponding solutions we are looking is first and third one is you have to design in a reasonable time and with less efforts. So how that is done, that we are going to see. And third one is you have to test it. Okay. Second one is related to architecture. Remember, second one is related to architecture. So architecture selection that depends upon the manufacturer requirement and existing material available, existing logic designers, existing dimensions of your device. So many parameters. Okay, speed, delays, everything, because speed is the design constraint. So problem 1 and 3 are solved if you are following these strategies. What are the strategy? You can go for a top-down design approach. What is top-down? Consider your top module, take it a hierarchical fashion, its submodules, and finally to the least requirement. What is the least requirement? Your gates, your all gates. Together they build one logic function. Together all these logic functions, one more subsystem. Those subsystems together form your top module. So your design should not be randomly designed. Your design must be your design must be done in a top-down design approach. What is the top-down design approach? It must be using some CAD tools, and your any IC design must be considered in a top-down design approach. Then you have to partition the system sensibly. What is partitioning the system sensibly? You have to So your design, so your design must go for a top-down design approach, and you have to partition the system sensibly. What is sensibly means which systems must be placed at what position so that delays are less, and aiming for simple interconnections, going for high regularity within subsystem, generate and then verify each section of the design. So even if you have analyzed your top model in terms of subsystems, they must be verified for each section, and high regularity within the subsystems, and simple interconnections. And you also see that you devote certain portion of the chip for, you have to devote significant portion of the chip for testability, because now present ICs, they are having automatic test pattern generator within the ICs. Once you enable them, the automatic test patterns are generated and entire IC is tested. So such design logic must be embedded in your IC, and the architectures that allow design objectives and high regularities in realizations. So you have to also select the architectures. Though the first topic, problem 1 and 3 are solved by uh, doing the design in a reasonable time, and with reasonable efforts, and also testing the design, are done by top-down design approach, partitioning the system sensibly, aiming for simple interconnections, high regularity within the subsystems. So you should not go for redesigning different logics. So certain portion of the designs which you have used earlier, they can use again in the within the design. Okay. And certain portion of the chip must be readily available for testable logic. And you have to select architectures that allow design objectives and regularity in realization. So this is the design consideration for your IC and subsystems. So this is the illustration of design process. You have to go for a structured design with the concept of hierarchy. Complex functions must be divided into subfunctions. So we'll see this process. So how that is possible, we'll see now. So for subsystems and IC design, we are covering three problems. One is you have to design the system in a reasonable time with reasonable efforts, select the architectures which can use all advantages of VLSI technology, and third one, you have to test it. Okay. So for this, we have given a solution is you can go for top-down design approach, and you can go for partitioning the system sensibly, because certain systems design clock require clock, and if clock is placed at a different place, that must be routed throughout all the subsystems, and it creates delays. So unwanted parasitic elements will be created. So all that is the design aspect. So partitioning the system sensibly, seeing that less interconnections are there, and highly regularity is followed in the design, and you can generate and verify each section of the design, and also what are the testable logic is there. That testable logic must be provided for each chip, and architectures allow regularity in the realization. So after this, we are seeing that the design process, you can go for you can go for uh, design process, the structural design. So whatever top down we are telling, that is called structural model. Structural model, it tells that for a half adder, the subsystems are an XOR gate and AND gate. XOR gate implementing some function, AND gate implementing OR operation. So that is structure design must follow the hierarchy. So top model is half adder, sub models are XOR gate and AND gate. So, and this complex function must be divided into sub functions until you get the leaf cells. What is the leaf cells? The basic gates. And that process is called top-down design. And as system complexity increases, various different factors must be considered in its organization. And why we are going for this coupling method is by using this coupling methods, you can see that your submodules interact, and you have to place those subsystems which are frequently required to exchange the data, such as your memory. Memories require that, and processor requires data to be exchanged between memory and to be written and to be read from the memory. So your memory cannot be placed in a distance place from the processor. So that is called proximity. So those components having interaction must be physically proximate, means they must be very near, and concurrency should be exploited. All gates of the design use it is desirable that all gates on the chip do useful work most of the time. So concurrency should be exploited. So what is concurrency in the sense is uh, if certain subsystems are uh, implemented, doing the processor is working on it and they are exchanging the data with the memory or thing, see that the subsystem, some other logic is parallelly done in the other subsystems. So not that all subsystems are placed idle if one of the design is going on. So when you go for multiprocessor and multi processing systems, multitasking systems, this is done. So your subsystems are having the concept of concurrency, so that all gates on the chip do useful work most of the time. And the technology changes so fast, you have to adapt to the new technology within a short time. So because a designer starts designing in the CAD tools, he writes a code for a certain logic, then he checks the functionality of the design, then he can go for implementing in a standard design, or he can create its own IC. So whenever there is a change in the design concept, see that wherever you make changes, those changes are easily adaptable to the new logic, and that is done in a short duration of time. So certain design process considerations are covered here, where you have to see that your subsystems are meeting the 5 entities. So for which we are showing this architecture. So generally while designing, what are the approaches used at different stages is other than CAD tools, we can also use in the CAD tools or in the manual designing, we can use the circuit symbols, logic symbols, stick diagrams, layouts, the architectural block diagrams, and floor planning. So these are the tools or the approaches used for different design stages. So here we consider the digital processor. Digital processor structure. You can see there are there is a 4-bit arithmetic processor. So this 4-bit arithmetic processor is having 4 submodules. So the subsystems here shown are memory, ALU, and registers. They are implemented as a data path. Then there is a control block. There is an input-output block, and this data bus. So if you see in the data bus is having a bidirectional view between memory and data bus, ALU and data bus, input-output devices. So the input-output devices will write the data onto the data bus, and that data is sent to the corresponding memory or to the ALU. And this ALU will receive the control signals. So there is a control bus connected to the ALU and the control unit. So if you see, based upon the data written by the programmer, the input data, the input onto the input lines, onto the data bus, it receives some, because entire data is sent as a packet. So in which certain portion is data and certain portion is control signals. Based upon the logic operation and operands, a control signal is generated. So if you see in the below line data bus, there is one arrow mark pointing to the control block. So that control block receives certain stimulus from the input. Based on the requirement, it generates one control signal either to the address bus or to the control bus. And based on that, address sent to the memory or input output. So if your data is given to your output devices like a monitor or any printer, it is connected to your input output devices. So address bus, control bus, and data bus. These 3 buses together with the subsystems, and this is its data path architecture. So all control lines will run vertically, and all data lines and address lines will run horizontally in the design. So here it is a 4-bit arithmetic processor. It is getting an input called data in. So that block tells it is a bus. So it can be it is a 4-bit. So 4-bit data, it is fetched to the data path. Data path consists of your ALU and registers. So ALU nothing but arithmetic logic unit, and also temporary storage of operands. So that is your registers. Then control input, together it generates data out. So that is the data path implemented in a hierarchical design. So from layout side, what are the considerations for 4-bit arithmetic processor? So already we have seen the design rules in layout. So any metal can cross your poly or diffusion. So any metal can cross poly or diffusion. Poly crossing diffusion. So you can know poly is a red color, diffusion is a green color or yellow color, depending upon, this is for our stick diagrams. So for stick diagrams, poly crossing the diffusion means it is a transistor. So a red color crossing a green color represents an NMOS transistor. A metal blue color can cross poly red color, or a metal can cross a diffusion. So into the layers of the silicon, what are the design considerations is for a 4-bit arithmetic processor, metal can cross poly or diffusion. Poly crossing diffusion forms a transistor. Whenever lines touch on the same level and interconnection is formed. Simple contacts can be used to join diffusion or poly to the metal. Buried contacts can be used to join diffusion and poly. And the same processes can be used for second metal. Two metals can be joined by a via, and each layer has particular electrical properties. For CMOS layouts, N diffusion and P diffusion wires must not directly join each other, nor they may cross either P well or N well. So these are the considerations done at the layout level. So our first design is a barrel shifter. So first we are covering what is a shifter. So design of a 4-bit shifter. What is a shifter? If you consider an n-bit shifter and any general purpose n-bit shifter, is should be capable to shift incoming data by n-1 places. So if you consider 4 bits, it will shift n-1 places, means 3 bits. 3 places it will shift in a right or left shift direction. And further specifying that all shifts should be on an end-around basis. What is end-around basis? Any bit shifted out at one end of the data word will be shifted in at the other end. So if you do left shift, the left generally data is represented as MSB to LSB. So for a 4-bit, MSB, A3, A2, A1, A0. So if do left shifting, A3 will do an end around and it will be placed in the rightmost place. So any bit shifted out at one end of the data word will be shifted in at the other end of the word. If you do this end around designing, the problem of doing right shift and left shift is greatly eased. So the shifter. So if there is a shifter, you have to give the input to the shifter. So that is input you can give to the shifter from a 4-line parallel data bus. Say a 4-line data bus will give input to the shifter, and that shifter can give 4 output lines for the shifted data. So once it is shifted, you have to read that data. So see in your general analysis, your microprocessor, ALU, control unit, all this they will be doing some computational. In that, addition is one process, logical operation is one process, shifting is one process. So when we are coming to shifting, once you do 3 left shifts, whatever the data is there, that data is required for further processing. So for further processing, you have to see that the data is sent to the output lines. So the shifter must have input from a 4-line parallel data bus. It must have output. So 4 output lines for the shifted data. And every time you do the shifting operation, so means of transferring input data to the output lines by doing shifting from 0 to 3 bits. So the 4-bit data can be shifted in how many times? 0 to 3. You can do no shift. 0 shift is no shift. 1 shift, 2 shift, 3 shift. So 0 to 3 shifts can be done. So logical shift, arithmetic shift, and rotate. These are the 3 shift operations. So we are generally covering a shift operation. Then we'll see what is the difference between normal shifting and barrel shifting. So what is a logical shift? Once you shift number left or right, it is going to fill with zeros. That is logical shift. If you do left shifting, what is happening? MSB is discarded. It is not considered, and second bit comes to the first bit. Like that, shifting is done, and the least LSB position 0 is selected. So if you see here 1011 LSR means logical shift right by 1 bit. LSR logical shift right by 1. If you are doing right shift, what is happening? 1 is placed in the here. Okay. Logical shifting by right. So this here once to right shift, this one is eliminated and 101 will come into the next position. In the MSB position, 0 is placed. For 1011, for 1011, logical shift left by 1. So if you are doing logical shift left by 1, you are doing left shift. So 011 will come and be placed in the 3 places and the MSB 1 is eliminated and LSB bit 0 is placed. MSB bit 0 is placed. Here MSB bit 0 is placed here. So here right shift 0 is placed here. Left shift 0 is placed here. So that is called logical shift. What is arithmetic shift? Shift number, you are going to shift number of times left or right, but right shift follows sign extension. So arithmetic shift right by 1 position. So we are doing the right position. So 1011 becomes again 101. So because they are moving to the right side, but MSB bit will do the sign extension. Sign extension is it is placed as 1. Next 1011 arithmetic shift left by 1 position. Once you do arithmetic shift by left position, so 1 is eliminated, 011 is placed in the 3 places. This 011 is placed in the 3 places and again in the LSB 0 is placed. And next we are doing a rotate operation. This logical shift, arithmetic shift and rotate, they all come under shifting operations. So when you do rotate, whatever the last bit in earlier 3 cases, that is placed in either MSB or LSB. So if you see 1011 rotate right. So once you are rotating right, 101 is placed. First 3 bits 101 are moved to the right side. So they are placed as 101. But whatever the LSB earlier it was last, that is again placed in the MSB place. So you see 1011. This first last one is coming and placed in the first position. Okay, last one is coming and placed in the first position, and the remaining bits will shift by 1 bit. So like that, this one is coming and placed here, so it becomes 1101. Similarly, 1011, once you do rotate operation left. So once you are rotating, 0 comes in the first place, 1 comes in the second place, again 1 comes in the third place. In the fourth place, what it will come? The first bit. So the first bit will rotate. So you see 0, 1, 1, 1. So this is its rotate operation. So for performing this rotate operation by our design, we are considering your design as a 4x4 crossbar switch using MOSFETs. So one of the MOSFETs is on and off such that you can do the shifting operations, either left or right. So vertically, our input lines IN0, IN1, IN2, IN3 are placed. Horizontally, out3, out2, out1, out0 are placed. And wherever there is an interconnection between input and output, there is a MOSFET with its gate. There is a MOSFET, another gate. So like that, you require 16 MOSFETs. Okay. So once this MOSFET is on, example, wherever I'm keeping cursor, if this MOSFET is on, what is happening? IN0 is connected to out3. Okay, IN0 is connected to out3. So based upon the design requirement, you have to see that one of the switches is made on and you can do left shift and right shift. That will cover in a further class. And this is the same design. Horizontally, inputs are given as A3, A2, A1, A0. So that is the data wire. So I told now in our subsystem design, we follow data path and hierarchy. Data path consists of all the subsystems consisting of ALU and registers and other subsystems placed in a horizontal fashion, and your data lines run horizontally and control signals run vertically. So that is data path architecture. So here if you see, for each MOSFET, there is a control signal called SH1, SH2, SH3. So a specific path is followed. This is the design of a 4x4 barrel shifter, which is to be covered in further classes. So we'll see the explanation of barrel shifter further classes. So we'll again listen to these topics, whatever we covered till now. So you can see here horizontally input, and there are at the output side there is a buffer, then B3, B2, B1, B0. But this is the design of a barrel shifter. That's why if you see this logic explanation, if you see SH1 is connected to first one, SH2 is connecting this MOSFET and this MOSFET. So you can analyze, you can only see that these are control lines. These light color lines are control lines. These light color lines are control lines. These light color lines are control lines. So this light color lines are control lines. So here SH3 connecting this MOSFET, this MOSFET, this MOSFET. SH not connecting all these MOSFETs.
And how it is different from BiCMOS. So why we are going from BJT to MOS to BiCMOS? Because these technologies are implemented in an integrated circuit. So you know integrated circuit is a miniature electron chip consisting of active and passive components fabricated under thin layers of silicon. So various process steps you have seen like oxidation, lithography, diffusion, ion implantation, and metallization. And we also covered a topic called NMOS fabrication, where the various layers of silicon using these fabrication steps, we have implemented an NMOS, two N plus regions in a P-type semiconductor, and PMOS, P plus regions in an N-type semiconductor, and CMOS, complementary MOS, consisting of NMOS. So it is implemented in 4 different techniques, like N-well process, P-well process, printed process, silicon on insulator. So our first part of our VLSI design, we have covered fabrication of MOSFETs into the layers of silicon. Next, we have studied the electrical properties of MOSFET, where how MOSFET parameters are affected. So the first part we have studied is MOSFET operating in 3 regions: cutoff, linear, saturation, corresponding current relations. What is the threshold voltage? With respect to threshold voltage, what is body effect? And the electrical properties are transconductance, output conductance, figure of merit. So this will decide the MOSFET features. And using a MOSFET, we have created a switch logic, a pass transistor. So the drawback of unable to transfer logic 1 for NMOS, logic 0 for PMOS. So there we have covered transmission gate, CMOS bidirectional switch, where NMOS and PMOS are connected at both ends, and it is acting as a bidirectional switch. So the basic gate we covered is an NMOS inverter, a NOT gate. Using an NMOS inverter, we have implemented pull-up to pull-down ratio with pass transistor and without pass transistor. So, and the another topic we covered is an inverter designed using various pull-ups. So you can design an inverter with pull-up as a load resistance RL. Another is instead of load resistance RL, you can go for an NMOS, or you can go for a depletion device, or you can go for PMOS. So if pull-up is the depletion device, that is totally NMOS device. If pull-up is a PMOS, it is a CMOS inverter. So there are 3 types of inverters. Inverter implemented with only NMOS, with CMOS. So the CMOS means you have both PMOS and NMOS. Then a CMOS at the load side, you have a BJT in order to increase the output drive current. So that is your bi-CMOS inverter. So this covers the unit 1. In unit 2, we have seen for the unit 2, we have seen how to create a VLSI design flow, how you start from your logic to the implementation of an IC. So various steps we have studied, and there we have seen your logic can be implemented by various technologies. So CMOS logic we have seen. Then a fabricator has to form various layers on the silicon by using one diagram called stick diagram or layout diagram, and it has some basic rules. So the minimum transistor length, width, dimensions, so that no parasitic elements are created after fabrication of your design into the layers of silicon. So small examples like layout diagram for a NOT gate, AND gate, NOR gate are covered in the syllabus. So using both technologies, either NMOS and CMOS. And if you are going for 2 scaling of technology, so now presently it is 14 nanometer technology. Initially it was some around micrometers to nanometers. So every time when we are scaling, we are reducing the power requirements, length and width dimensions, and we are going for miniaturization of MOSFET so that you can integrate large number of MOSFETs into an IC. So there you can see alternate to your NMOS and CMOS logic, you can go for various technologies so that the basic requirement of IC designing is low powered ICs, high speed ICs, less area ICs. So these 3 are compulsory. So main parameter is speed. So we want faster ICs so that you can build a large number of multimedia applications. Everywhere digitization is is done, and this is because of your ICs. So there we have studied switch logic, then the alternate gate circuits like pseudo NMOS, differential cascade voltage switch logic. Okay, so after covering this in this, we have seen what is a delay, how delay is affected at the output, and is a delay, and how to drive large capacitor loads, what is fan in, what is fan out, and how you form the layers so that you can reduce the parasitic elements, and what is the wiring capacitance. So this covers up to unit 3. Now your next part is your unit 4. So already you know what is a MOSFET and how to control the length and width of your MOSFET so that you can meet your requirement. So you want to increase the current driving capacity, or you want a faster design, or you want more number of logic gates and more number of transistors implemented on a small area. So how to increase the speed, how to increase your its transconductance. So that is related to your MOSFET designing. So there is one designer who controls he's called circuit designer. He controls the parameters of MOSFET. So after he does the actual designing of MOSFET, then using that MOSFET, you can connect them in a fashion to create one logic, such as your NAND gate and NOR gate. So those are logic designers. So once logic designer does his design part, implementing one digital circuit, whether combination or sequential, and implementing a very big design. Okay, so the next requirement is the layout designer. This layout designer is going to create a layout of the design and give it to the fab unit. So finally, after IC is fabricated, it is the testing part. So test engineer. So there are various levels of positions for a designer. So here in your unit 4, we have to see that because already you have created your MOSFET with the required parameters, less area, high speed, low power consumption. But that does not satisfy your total IC. So total IC must have these characteristics when its subsystems are meeting the characteristics. So we are not looking from transistor, we are looking from logic. We are not only looking for logic side, we are looking from the subsystems. So if you consider a microprocessor, how a microprocessor can meet an IC. Microprocessor IC can meet your 3 characteristics. What are they? Less area, low power consumption. So these all 5 characteristics by argument if it's subsystems, like your subsystem of a microprocessor is ALU, subsystem of a microprocessor is a control unit, subsystem of a microprocessor is memory. So these all subsystems must also have these characteristics. So at data path level, so how data is transferred into the various layers of your silicon from one system to another system. So how control signals are routed, that is studied here. So that we are following a data path logic for all subsystems, and each subsystem must be optimized for these parameters. So that is your unit 4, and the system level must be optimized. So what can be the subsystems? A subsystem can be a shifter, a subsystem can be a adder, a subsystem can be a ALU. So an ALU can have data path and control path unit. A subsystem can be a comparator. A subsystem can be a parity generator, 0-1 detector, multipliers, counters. So these all subsystems are used in different designs of your IC. Some ICs require only shifting operation. Some ICs require only addition, or together combination of these subsystems, they implement one logic. So other than not only combinational part, we may require to implement some sequential systems. There you require memory. So a subsystem optimized for its memory as SRAM, DRAM, ROM, and serial access memories. So up to this is unit 4. So these contents must be studied in your unit 4. So we are going to see the first subsystem. That is your unit 4. It is your subsystem designing. So what is subsystem designing? If subsystems are optimized for all the 3 parameters, the major parameters like area, power, and speed, then its cost will be less. It produces high performance. So looking into this point, first we consider the objective. So we have to take a design consideration. What is the problem and what is the solution? So what is the problem when you go for subsystem design and how it is resolved? So what is the basic design process? So we will cover a digital process structure, and it has some data path architecture and bus architecture and various subsystems. So the subsystems studied in unit 4 are shifters, adders, ALUs, multipliers, parity generators, comparators, 0-1 detector, counter. So counter means synchronous counter, asynchronous counter. So it is not like the same like your switching theory or digital logic. Only thing is here we are going to see the optimized designs. So what are the general considerations? So lower unit cost. So you are going to optimize your subsystems, and the requirement is lower unit cost and they are higher reliability. So reliability means it's a high performance, low power consumption, lower weight, lower volume. Better performance, enhanced repeatability. Enhanced repeatability means you can do small changes and reproduce the designs. So design period must also be reduced. So you should not take long time because there is a competition from another vendor. So you have to see that your subsystem is taking reduced design period. So what are the problems while designing subsystems is you want to design a complex system in a reasonable time and with reasonable efforts. And the architectures you have to select is they must be such that they take full advantage of your VLSI technology. And you have to test these large complex systems once they are implemented on the silicon. So your subsystem design, the basic objectives, design considerations, the problem solution, the basic digital process structure, data path bus architecture, and the subsystems to be studied in unit 4 are shifters, adders, ALUs, multipliers, parity generators, comparators, 0-1 detector, counter. So these are the design considerations: lower unit cost, higher reliability, low power dissipation, lower weight and lower volume, better performance, enhanced repeatability, possibility of reduced design time. And here, if you want to go for complex system within reasonable time, what is the issue is you have to design complex systems in a reasonable time, and those architectures must take full advantage of VLSI technology. And once they are implemented on the silicon, they must be tested. So the first problem is you have to design complex systems in a reasonable time and with less efforts. with reasonable efforts. And also you have to test it. So the first and third problems are greatly reduced with certain aspects which are given below. So if you practice these methods while designing your subsystems, your first part is met. You want to design your subsystems and together the complex system in a reasonable time and with reasonable efforts. And also they must be easily tested. So that is possible when you go for first method called top-down design approach with adequate CAD tools to do the job. So what is top-down design approach? You start with the microprocessor, you draw in a tree fashion what is the next subsystem. ALU, control unit, memory. Next ALU, what is the next design? Arithmetic unit, logic unit. Next control unit, what is the design? Control signals for controlling your shifters or some other subsystems. So wherever you require control systems. So you have to again sub-design those control blocks and memories, RAM or ROM, and again how they are implemented. So you have various methods of memories. So once you have this top-down design approach, you know what are the down designs. Once you have a down designs, what is the down part? Then part is arithmetic unit and logic unit. And arithmetic unit adders, okay, multipliers, some arithmetic operations, logical operations. So those all are implemented and they are combined to make a ALU. All control blocks are controlled to make a control unit, and all memories together they form your memory unit. And again together they all become your top unit microprocessor. So there must be some design methodology. What is the design methodology? You have to go in a flow. First you have to analyze what is your top module, what is the sub module, what is the next sub module, and how you start designing. So you can go for top-down design approach by using some CAD tools. Then partition the system sensibly. So when you partition your design, you have to see that which portion of your design you require to be kept in a region of another design, because if you are partitioning and designing the blocks and you are again combining them, there may be a problem of creating more delays. So you have to see that delays are less because faster circuits are designed when you reduce the delays. So partitioning the system sensibly and aiming for simple interconnections. So your subsystem, because you don't know what is each subsystem, you know only top module. So when you analyze its sub modules and its sub modules, and when you want to optimize the design, you have to see that they are having very simple connections. The key subsystems is having very simple interconnections and high regularity with subsystems. Generate and then verify each section of the design. So this first point, the two issues of designing in a reasonable time and testing is resolved if you practice these methods. The first method is top-down design approach, partitioning the system sensibly, aiming for simple interconnections, high regularity within subsystem. You have to generate and verify each section of the design. So by using this first method, your design aspect is ready. Once design is ready, what is the next part? It is implemented, then it is tested. Okay. So second part is you have to devote some significant portion of your total area. See now various test techniques have come where within an IC you have certain portion kept for test pattern generators. For each portion of your design, this test pattern will generate the inputs and it will see that for all possible combinations it is tested. Like you have a half adder, 2 input adder. So the test pattern for the generated is 0, 0, 0, 1, 1, 0, 1, 1. So for all these possible combinations, your chip is tested whether its output is correct or not. Then only that design is sent to the market. So you have to devote significant portion of total chip area to test and diagnostic facility. And you have to select the architectures that allow design objectives and regularity in realization. So why it is regularity in realization is this is one of our objectives. You can't take any general architecture because that architecture or this whatever the design you implement, the design it must be again maybe reused in its further designs. Okay, so that aspect is must be considered. Random logic you cannot select, so you can have an objective such that you can go for realization with the regularity of designs. So what is the regularity of design means? If you want certain portion of the design to be implemented, so you can go for regularly implementing that using only one specific design. So that helps in reducing the design time. So by using these three methods, you can solve our first problem and third problem. So what is the illustration of design process? Structured design begins with the concept of hierarchy. So where I told no top-down design, a subsystem design done by using top-down design implements hierarchy. So you have to design your top module into sub-functions and finally the leaf functions. And this process is known as top-down design. So any top-down design methodology will implement the hierarchy. So as your system complexity increases, you have to consider different factors related to its creation. And when you couple, okay, coupling can be used as a measure of how much submodules interact. So what is coupling means? You are, as a designer, you know for one logic you require one IC and you analyze its subsystems and its leaf cells. And you have to see that which subsystems are coupled to another subsystems and how they are interacting. So this is for controlling the interconnects. So we have to go for simple interconnects. So if you see the point, it is crucial that components interacting with high frequency be physically proximate. So what is physically proximate? So one adder or one sequential circuit requires that regularly it has to fetch data from a memory. So that memory component must be near to this system so that it can regularly fetch the data. Okay, so physically proximate means nearness. So all subsystems which are interacting regularly during its operation must be placed nearby such that you can reduce the long interconnects because long high bandwidth interconnects can be reduced. Concurrency should be exploited. So concurrency should be exploited. It is desirable that all gates of the chip do useful work most of the time. Okay. And because technology changes so fast, your design must be ready to adapt.
Of data shifter. Any general purpose n-bit shifter should be able to shift the incoming data word up to n-1 places in a right shift or in a left shift direction. The given shifter is end around shifter. It means any bit shifted out from one end is available to the other end. So basically, we are going to rotate the data. If one data bit is coming out from the right side, it should go to the leftmost bit. In this video, we are going to discuss 4-bit data shifter. To understand the basic operation of 4-bit data shifter, let us first try to understand 4x4 crossbar switch. It has 4 inputs, I0 to I3, they are running parallel to each other, and 4 outputs O0 to O3, they are also running parallel to each other. None of the input and output lines are connected. Now, if we want a zero shift, we require 4 transistors. Their gate controls are 0, 0, which connects the input 0 to the output 0. Similarly, gate control 1, 1 connects input 1 to the output 1. Gate control 2, 2 connects input 2 to the output 2. Gate control 3, 3 connects the input 3 to the output 3. So if we apply high gate input to these 4 transistors, we will have 0 data shift. So whatever input we are applying, the same output we will be getting as shown in the table. Now let us suppose we want 1 bit right shift. So input 0 must be available at the output 1. So for this we require the transistors 0, 1, 1, 2, 2, 3 and 3, 0 in on state. Similarly, for 2-bit shift, input 0 must be available on output 2, and for the 3-bit shift operation, input 0 must be available on output 3. So each transistors are represented by different color for better understanding. The main disadvantage of this circuit, we have a 16 transistors and each transistor is having a independent gate connection. It means we have a 16 different input, which makes the circuit working very complicated. Now let us assume a situation when all the inputs are high. If that is the case, it means all the transistors are on and all the input lines are connected to all the output lines, and hence the meaning of data shifter is lost. So now we will see how to overcome this, and that will lead to the topic barrel shifter. We will try to understand the working of 4x4 barrel shifter with the help of given table and the circuit. Here we have taken 1, 0, 0, 0 as an input, which is decimal equivalent of 8. Now we want 0 shift. So we have 4 input and 4 output, and to connect the input to the output we require 4 transistors. So the control signal or the gate signal of each transistor must be shorted. So whenever we make gate input 0, 0 high, it makes the all gate terminal of transistors, that is 1, 1, 2, 2 and 3, 3 high, and all the transistors are on at the same time, and they connect input 0 to the output 0, input 1 to the output 1, and so on. For 1 bit right shift, the transistor 0, 1, 1, 2, 2, 3 and 3, 0 must be on, and hence we have shorted all the 4 gate terminal of the given transistors as shown in the figure. It will result in 1 bit right shift. So if we will compare the 0 shift data given in the table and 1 bit right shift data, so we had input 8, and after 1 bit right shift we are having a data which is equivalent to 4. So we are able to divide it by 2. Similarly, if we want to perform 2 bit right shift, transistor 0, 2, 1, 3, 2, 0 and 3, 1 must be on. Therefore, we have shorted the gate terminal of all the 4 transistors. To perform 3-bit right shift operation, we have made transistor 03, 10, 21 and 32 on by shorting their gate terminal. If we will bring all the 16 transistors in a single diagram as shown in the figure, it results in 4 cross 4 barrel shifter circuit, which is capable of performing 0 to 3-bit shift operation and is having only 4 control signals, which is very less compared to 4 cross 4 crossbar switch. Thank you.
This was regarding subsystem design and the various subsystems and the barrel shifter. So coming class will start again with barrel shifter. So first we'll see what are the shifters, then what is a barrel shifter. So different examples, left shift, right shift will cover. So for today class, I want to conclude. If you're having any doubts, you can ask me.
Sir, attendance download.